We're going to continue our discussion of inner products. So let's remind ourselves where we were. Last time we talked about the notion of an inner product on a vector space. You have two vectors x and y, and you define an inner product, which is written this pair x and y. It's a number. And by definition, an inner product is required to be symmetric, bilinear, and positive definite. And we saw, of course, the basic prototype of this is the usual dot product. You take the inner product of x and y to be x dot y. But other inner products are possible, and we're going to be talking about some other ones and their properties. And when you have an inner product, you also have the associated norm, which is you take the inner product of x and take its square root. And that's the length of x, or the norm of x. I want to do one more example before I go on. In R2, consider the following definition. Define the inner product of x and y with x prime and y prime to be the following. Take 2x x prime plus 2y y prime minus xy prime minus yx prime. I claim that this is an inner product. It's quite obvious that it's symmetric. It's almost as obvious that it's bilinear. It's easy to check that. The main thing is it's not obviously positive definite. That's where you need to be careful. Why not? Well, let's see. What is the inner product of a vector xy with itself? What you get is 2x squared plus 2y squared minus 2xy. And because of this minus sign, it certainly looks possible that for some choice of x and y, this could turn out to be negative. It almost looks like it would, but it's not. There's an identity. You can rewrite this thing by completing the square as x squared minus y squared plus x squared plus y squared. Notice that when I write it this way, it's the sum of three squares. And the only way, then that's always non-negative. So in spite of the minus sign, this is a perfectly good inner product. Okay, let's go on now and talk about some inequalities. So these are some properties that hold of any inner product. And the first one is a very famous inequality. It has a name. And it's called the Cauchy-Schwarz inequality. And in spite of its simplicity, or in fact, because of its simplicity, it's actually a very powerful inequality. It's quite ubiquitous and comes up in lots of settings. And it says the following. If you have any inner product, so we have a vector space V with an arbitrary inner product. Then the statement is that if you take the inner product of any two vectors V and W, then that's guaranteed to be less than or equal to the length of V times the length of W. All right. Now, the left-hand side is the the inner product of two things. It could conceivably be negative, in which case this would be obvious, because the right-hand side is positive. But in fact, it's even true if you put an absolute value on the left-hand side. The absolute value of this inner product is less than or equal to the length of V times the length of W. That is the Cauchy-Schwarz inequality. And here's not really a proof, but I'm going to call it that, or put it in quotes. And this is really how I recommend that you remember this inequality, because in the case of the usual dot product, it's just the law of cosines. So the law of cosine says that the dot product of V and W is the length of V times the length of W times cosine of theta. And let's compare this to this inequality that we have up above. Well, on the left-hand side is the absolute value of V dot W, and the right-hand side is the length of V times the length of W, and then this extra term is cosine theta. And of course, the absolute value of cosine theta is less than or equal to 1. That's the key point here. So this box in blue says that these two things up here, the v dot w on the left-hand side and the product of the lengths on the right-hand side, they're the same up to this number of absolute value less than or equal to 1. So that says that you have this inequality in the Cauchy-Schwarz inequality. The left-hand side is the right-hand side times a small number. Okay, so let's look at a simple example. Let's take v to be 1, 2 and w to be 3, 4 and use the usual inner product. Then 1, 2 dot 3, 4 is, well, let's see. It's less than or equal to the length of 1, 2 times the length of 3, 4. And let's see. The left-hand side is 3 plus 8. And the right-hand side is, let's see, the square root of 5 times the square root of 25. Is that true? Let's see, the right-hand side is 5 radical 5. So I'm claiming that 11 is less than or equal to 5 radical 5. Gee. Well, let's square the left hand. Let's square both sides to check. I'm claiming that 121 is less than or equal to 25 times 5, which is 125. There you go. It's true, but not by a lot. It's useful inequality because it's subtle. It's not obviously true, but it's true. Here's another example. Let's again in R2. Let's actually specialize just like the previous example. Take v to be 1, 1 and w to be any vector a, b. Then I'm claiming that the dot product of 1, 1 and a, b is less than or equal to the square root of 2 times the square root of a squared plus b squared. And let's see, the left-hand side is a plus b. So let's see. Let's square both sides again. I'm saying that a plus b squared is less than or equal to 2a squared plus b squared. Well, it's true. I'll let you stare at that for a minute and convince yourself. You could do some algebraic manipulation and see that that's true, but it follows from the Cauchy-Schwarz inequality. And let's just plug in some numbers and see. A is equal to 1 and b is equal to 3, for example, gives the claim that 16 is less than or equal to 2 times 1 plus 9. Well, that's true. 16 is indeed less than or equal to 20. Okay, another part of the theorem deals with the equality part. So the theorem itself says, as I stated, it says that the absolute value of the inner product of v and w is less than or equal to the length of v times the length of w. And when are they equal? Well, it's very hard for them to be equal. The only way that they can be equal is if v and w were parallel, which is to say v and w are scalar multiples of each other, and they're in the same direction or possibly in opposite directions. And well, let's see. Let's just check if you take two vectors that are multiples of each other, and you take their inner product. Well, the c pulls out, so you get c times vv. And that pulls out with an absolute value. So the left-hand side is the absolute value of c times the inner product of v and v. The right-hand side is what? Well, it's the length of v times the length of w, which is c times v. And that's the length of v. And the length of a multiple pulls out, the c pulls out with an absolute value. And sorry, these w's are supposed to be v's here, excuse me. And that gives you the absolute value of c times the length of v squared. And let's see, the left-hand side is the same thing. So that's one direction. That's one direction of the if and only if. If they're multiples of each other, then you have equality here. And really, why is this? Well, the extra term in the law of cosines is this cosine. And so these things are going to be equal if and only if the absolute value of cosine is equal to 1, which is to say that the angle between them is 0 or pi. Okay. I used a little bit about some formal properties there. Let me mention those specifically. We know that if you, by the bilinearity property, if you multiply an inner product by a constant in either term, it pulls out. The result is that if you if you multiply a vector by a constant, it pulls out. Well, it can't quite because it has to be positive, so it must pull out with an absolute value. If it didn't, then you could have a negative number here, and that would not be okay. So let's just see. For example, if you take the length of minus v, what do you get? Well, it's the square root of minus v, inner producted with minus v, and the two minuses pull out and cancel to give plus, right? So you can just cancel them, and that's the same thing as the length of v, inner product of vv, which is the length of v. So the minus 1 pulls out with an absolute value of minus 1, which is 1. And more generally, if you multiply a vector times c, what you get is the inner product of cv with itself, and each of the c's pulls out of this, and so you get, inside the square root, you get a c squared. So you get a square root of c squared times vv. And what's the square root of c squared times vv? Well, it's the square root of c squared times the length, the inner product of v with itself. And what's the square root of c squared? Well, it's c. Except careful, it's the positive square root, so it's not just c, it's the absolute value of c. And this becomes the length of v, and so you see that indeed this c comes out with an absolute value. Okay, another important inequality involving inner products is the triangle inequality, and everybody knows this one. In the usual picture, if you have two vectors and you add them, we know the shortest distance between 2 points is a straight line. And the theorem is simply that the length of v plus the length of w, the length of v plus w is less than or equal to the length of v plus the length of w. So in the usual dotted product, this is just a familiar from elementary elementary geometry. And you have equality here if and only if w is a multiple of v, and in this case the w has to be a positive multiple of v. So there's no cancellation. C is greater than or equal to 0. So that is to say they're parallel and in the same direction. So again, this is, I'm not going to prove this, but this is just the usual triangle inequality from elementary geometry. There's another item I want to cover now, which is the notion of orthogonal vectors. So what does it mean to say vector v is orthogonal to a vector w? You say v is orthogonal to w. Well, you have to tell me what inner product you're talking about. If you're in Rn and it's usual dot product, that's fine, but in general you have to specify. So you say with respect to a given inner product, and if you have an inner product, then you say two vectors are orthogonal if their inner product is 0. So this is a crucial point. There's the notion of orthogonal. There's not just one notion. It depends on which inner product you're using. And as always, the geometric intuition comes from the usual inner products. The inner product, the usual dot product of two vectors, is given by the law of cosines. And when is that 0? Assuming that v and w are non-zero vectors, that's when only if the angle is 0, and that is to say it's plus or minus 90 degrees, which is the usual notion of orthogonal, and sometimes we'll write v is perpendicular to w like this, and this is the picture that we have in mind. But again, keep in mind that this notion of orthogonal is not an absolute one. It depends on which inner product you're using.